Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll explain the shear stresses and angular twist induced on a stepped shaft due to torque acting on it. Let us consider a stepped shaft fixed at one end and subjected to torque as shown in figure. The free end at D is subjected to a clockwise torque 2T, and at the junction B there is an anti-clockwise torque T. Now at the fixed end also there will be a resisting torque based on the torque applied on the shaft. Now here clockwise torque 2T is acting and here anti-clockwise torque T is acting. So the resultant torque will be taking the anti-clockwise as negative, plus 2T minus T, you will have plus T, and that is resultant torque transmitted to this fixed end will be clockwise, so plus T. So at the fixed end you will have a reaction torque which is in the counterclockwise direction. Now if you have to find out the torque in any section, you can consider one portion. If you have to find out the torque in this particular section, you consider all the torques on right side. So if you take this section, the torque acting is T and 2T, but this T is anti-clockwise, this is clockwise. So you can take minus T plus 2T, or you get plus T. So the torque acting in the first section, that is torque acting in the section AB, is minus T plus 2T, you will get T. And for the second section, if you take a section and consider the torque on the right side, so you will have only one torque acting, that is plus 2T. Okay, even for the third section CD, if you take a section and consider all the torques acting on the right side, you will have only one torque 2T. So this way you can find out the torque acting in different sections. Now after getting all these torques in the various sections, you can find out the shear stress induced in these sections using the formula pi by 16 d cube into tau max. So torque is pi by 16 d cube into tau max. So for the first section you can substitute the torque and pi by 16 d1 cube into tau max in that first section. So different sections will have different maximum values of shear stress due to the torques acting, because they are having different diameters and the different torques are acting. So all these sections will have different values of maximum shear stress. So you can find out the maximum shear stress induced in various sections. Now to find out the angular twist, so you can find out the angular twist of one end with respect to the other. So to find out the angular twist of the ND with respect to the NDA, you can sum up the angular twist of on all the three sections. So this section AB, you know, that is in the first section you have a positive torque. The resultant torque is positive because 2T minus T, that is the torque acting in the first section. So you have a clockwise torque, resultant torque transmitted to this section AB is clockwise. So this will undergo a clockwise twist. Due to this clockwise torque, this will undergo a clockwise twist, and we will take the clockwise twist as positive. So the angular twist in the first section AB you can calculate as T1 L1 divided by J1 G1. And next in the section BC, again you are having a clockwise torque, because this 2T is the torque acting in the section BC. So that is also positive. Clockwise we can take it as positive. And CD also we have positive torque 2T. So find out the torque in each section, take clockwise as positive and anti-clockwise as negative. So in this case all the three sections are having clockwise torque. Now we can sum up the angular twist of each section, and then summing up all three sections you will get the resultant angular twist of the free end with respect to the other. So this represents the angular twist in the section AB, and second term is angular twist in the section BC, and finally you will get angular twist in the section CD. Sum up all the three, which will give the total angular twist in this shaft. Now let us work out a numerical example. A stepped shaft ABC is subjected to torques as shown in figure. Find the maximum shear stress induced in both the sections and the angular rotation of the end C with respect to end A. Given G is equal to 80 gigapascal. So this is a stepped shaft ABC, and it's subjected to torques at the various sections. So at A you have 100 Newton torque anti-clockwise, at B you have 300 Newton meter clockwise torque, and at C you have anti-clockwise torque of 200 Newton meter. Now the length of both the portions are same, 2 meter each. Diameters are 80 mm and 50 mm. Now material property G is given 80 gigapascal. Now you have to find out the maximum shear stress induced in both the sections and the angular rotation of the NC with respect to NA. So that is a total angular rotation in the shaft. Now first you have to find out the torque acting in both the sections, and then we can proceed. So we will find out the torque acting in the first section. First section, if you take, that is section AB, you consider the torques on right side. Okay, you don't consider this left portion. I am taking a section here. This is clockwise, so you can take plus 300, and this is anti-clockwise, so minus 200. So plus 300 minus 200, you will get 100. So that is the torque acting in the first section. So plus 300 minus 200, you get 100 Newton meter. And Newton meter you can convert into Newton mm by multiplying by 10 raised to 3. So which will give 10 raised to 5 Newton mm. So that is the torque acting in the section AB, or T1. I have taken it as T1. Now in the second section, if you take, it is only minus 200. So after taking the section, you are only considering the torques on right side. So it is only minus 200 because it is anti-clockwise. So minus 200 Newton meter, minus 200 into 10 raised to 3 Newton mm, or minus 2 into 10 raised to 5 Newton mm. So you are getting the torque in both the sections. First section is subjected to clockwise twist, whereas second section is subjected to anti-clockwise twist. Now shear stress induced in the sections you can find out. T1 is equal to pi by 16 d1 cube into tau max of the first section. Now T1 is 10 raised to 5, diameter is also known 80. Substituting that, you get the maximum shear stress as 0.994 megapascal. So this is the maximum shear stress induced in the first section. Now when you take the second section, T2 is equal to pi by 16 d2 cube into tau max of the second section. Now T2, 2 into 10 raised to 5. I am not putting the minus sign here because minus doesn't give any significance while finding out maximum shear stress. Okay, so I am not putting the minus sign here. A torque 2 into 10 raised to 5 and diameter for that section 50. You will get the maximum shear stress in that section as 8.149 megapascal. So this is the maximum shear stress induced in the second section, whereas in the first section is very small shear stress is induced. Now to find out the angular twist, you have to find out the angular twist in each section and add. But in this case, when you consider the twist in the first section is subjected to a clockwise twist, whereas the second section is subjected to an anti-clockwise twist. So here the twists are in opposite direction, so one has to be considered as positive. Either clockwise has to be treated as positive and anti-clockwise as negative, or opposite sign convention also we may use, but usually we can take clockwise as positive and anti-clockwise as negative. So torque, anti-clockwise torque In this case you have to substitute negative. In clockwise you should substitute as positive to get the sign convention for the twist. Otherwise, while adding, you will not get the resultant twist. So theta 1, the angular twist in the first section is T1 L1 divided by J1 G1. Now T1 is 10 raised to 5. Torque in the first section is 10 raised to 5. Length of the first section 2000. J value, that is polar moment of inertia. Once the diameter is known, you can find out the polar moment of inertia of circular section as pi by 32 into diameter to the power of 4. Diameter is 80 to the power of 4, and G value is given as 80 gigapascal, so 80 into 10 raised to 3, which will give the angular twist as 0.000622, and this will be in radian. So much radian is the angular twist in the first section. So that is plus. We got plus because this torque was clockwise, so plus. Now second section, you have torque acting as anti-clockwise torque. So here I am putting the negative sign. When you sum up, you should take the anti-clockwise as negative. So that's why I am putting the negative sign here. So minus 2 into 10 raised to 5 into the length is 2000. Polar moment of inertia is pi by 32 into 50 to the power of 4. 50 is the diameter there. Rigidity modulus 80 gigapascal or 80 into 10 raised to 3. By substituting that, you will get the angular twist as minus 0.00815 radians. So you are getting the angular twist in the second section, and that is anti-clockwise twist. Now to find out the resultant angular twist, you can just add the angular twist in both the sections. So that will give the resultant twist as minus 0.007528. So this is again in radian. You can convert into degrees by multiplying with the 180 by pi. So once you multiply with 180 by pi, you will get the minus 0.431 degree. So this will be the angular twist, and the resultant twist will be anti-clockwise, because we have used sign convention minus as anti-clockwise and plus as clockwise. So since the resultant twist we are getting minus, total angular twist is anti-clockwise, and it is 0.431 degree. Let us work out another example. A stepped shaft shown in figure is subjected to torques as shown. If the allowable shear stress is limited to 20 megapascal, find the minimum diameter d and also determine the total angular rotation of the shaft when this diameter is used for the shaft. G is given as 105 gigapascal. So you have to find out the minimum diameter d, keeping the maximum shear stress to 20 megapascal when these torques are acting on the shaft. So you have again a stepped shaft with the first portion having 1.2 meter length and second portion 0.8 meter length, and torque acting at the end A is 40 Newton meter anti-clockwise, at B 100 Newton meter clockwise, and at C 60 Newton meter counterclockwise. The second portion you have diameter d, and twice of that is the diameter of the first portion, 2d. If it is 10 mm, this is 20 mm, or if it is 20 mm, this is 40 mm. So that relationship exists. This double diameter is used for the shaft. Now you have to find out the diameter d. So once you get d, you can find out 2d. But finding out the diameter d, you have to see that maximum shear stress in the shaft should not exceed 20 megapascal while transmitting this torque. Now you have to find out the torques acting in the various sections. So here we have only two sections. Torque acting in the first section, by considering the forces on right side, we have plus 100, minus 60. So you will have plus 40. So in the first section you have plus 100, minus 60, plus 40 you will get. In the second section you will have minus 60 on the anti-clockwise torque. If you take a section here, only minus 60 is it. So you are getting the torques in both the sections, section AB and BC. So torque acting in the first section is plus 100 minus 60. You are getting 40 Newton meter, or 40 into 10 raised to 3 Newton mm, or 4 into 10 raised to 4 Newton mm. Torque acting in the second section is, when you take a section here, only force on torque on the right side you take, so minus 60 because it's anti-clockwise. So minus 60 Newton meter, or minus 60 into 10 raised to 3 Newton mm, it's equal to minus 6 into 10 raised to 4 Newton mm. So first section you have the relation T1 is equal to pi by 16 T1 cube into tau max of 1. So we know that torque acting in the first section 4 into 10 raised to 4 Newton mm, and pi by 16 into D1. D1 is diameter of the first section, is 2D is the diameter. So D you should find out, but whatever it's a D, 2D is the diameter of that portion. So 2D cube into tau max should be 20. So once you solve this, you will get D as 10.84 mm. So to satisfy the maximum shear stress 20 in this section while transmitting these torques, you should have a D value 10.84 mm, or totally 2D should be 21.68 mm. So this section should have 21.68 mm to satisfy this maximum shear stress 20 in that section. You cannot take immediately this diameter because second section may not satisfy this shear stress constraint for this diameter. So you have to check the second section to satisfy the maximum shear stress constraint in that section. The torque transmitted in that section is pi by 16 d2 cube into tau max of 2. Torque in that section is 6 into 10 raised to 4. Again I am not taking that sign because shear stress consideration sign is not required. You are only finding out the diameter to transmit that torque. So diameter is D for that section and maximum shear stress is 20. So by substituting that we will get a diameter as 24.81. So for satisfying the maximum shear stress constraint while transmitting these torques, second section should have minimum 24.81 mm diameter. So you cannot use this as a diameter. If you use this diameter, shear stress in the second section will be more. It will go beyond 20 megapascal. So you have to use 24.81 as a D. If you use 24.81 as D, you will have higher diameter here, and the diameter will increase here, but shear stress will be less than 20 megapascal. Shear stress will be within the limits, but you cannot use this diameter because if you use that diameter, shear stress in the second section will be more than 20 megapascal. So condition given is that shear stress in the shaft should not exceed 20 megapascal. So you should use D as 24.81. So D is 24.81 and D1 is 2 times D, that is 49.62. So the diameter of the first section, which is 2D, is 49.62 mm, and diameter of the second section is D itself, 24.81 mm. Now to find out the angular twist while transmitting this torque, you can use that dimensions to find out the angular twist in each section. Then you can add. So angular twist in the first section is T1 L1 divided by J1 T1. Torque transmitted is 4 into 10 raised to 4 Newton mm. The length of that first section is 1200. The polar moment of inertia is pi by 32 into d to the power of 4. Diameter we got as 49.62. Modulus of rigidity is 105 gigapascal. So 105 into 10 raised to 3. Substituting that, you will get the angular twist as 0.000768 radians. In the second section, the torque is minus 6 into 10 raised to 4. So I am treating this minus to get the sign convention here. Length is 800 and diameter is 24.81. So polar moment of inertia is 5 by 32 into diameter to the power of 4, and G 105 into 10 raised to 3. So you'll get minus 0.0123 radian. So in the second section you have anti-clockwise twist. Minus indicates anti-clockwise. Now you can add the angular twist in both the sections, which will give the total angular twist as minus 0.01153 radians. So this is equal to minus 0.66 degree. By multiplying with 180 by pi, you will get in degrees. So the resultant twist is minus 0.66 degree, minus indicating anti-clockwise twist. So the resultant twist, that is in both the sections put together, the shaft is undergoing an angular twist of 0.66 degree in the anti-clockwise direction. That's all for today. Thank you for watching.